Thank you for your kind introduction. And today and tomorrow, I'd like to talk about gravitational theories. So basically, this is an introduction to modified gravity. And actually, this subject is quite broad, so I cannot cover everything, apparently. So I can cover only a small subset of this broad subject. And this is contents that I decided to cover in this series of lectures. And so first, after a short introduction, I'd like to explain, of course, GR, because we want to modify GR, and without knowing GR is impossible. So I'll explain GR, and then its extension to higher dimension, which is called the level of gravity. And then the so-called parameterized post-Newtonian formalism. And then the effective field theory of scalar tensor theories and the mass of gravity and the Hodge-Lewis gravity, and then summarize this lecture. Okay, so these three are concrete examples, and these two kind of actually these three are introduction in a sense. Okay, so okay, let me start. Okay, so introduction. Okay, why modified gravity? So there are several motivations, but the first motivation comes from the mystery in the universe. So such as flattening galaxy rotation curves and living supernova, and these phenomena suggest that we need extra gravity or universe is accelerating. And so, by the way, IR means long distance or long time scale or low energy. Okay, and then so usually people try to explain these interesting phenomena by introducing new forms of matter, namely dark matter, and a new form of energy, namely dark energy. But when we consider history of the science, there was something similar in 19th century. And so that people discovered that the Mercury was doing something interesting, namely the appreciation of perihelion. And then some people try to explain this with, so to speak, dark planet. Okay, so which is named Vulcan, and some people even discovered it. Of course, the discovery was not the right one, and so the right answer wasn't the dark planet, and it was change gravity from Newton to GR. So considering this history, it may make sense to hope to address some mysteries in the universe by changing gravity. Okay, so that's one possibility, one motivation to think about modified gravity. Okay, so the mysteries such as dark energy, dark matter, inflation, Big Bang singularity, or maybe cosmic magnetic field. If we can replace some of them by modification gravity, that would be great. Okay. Also, the second motivation comes from our hope to unify quantum theory with the general relativity, namely quantum gravity. Okay, probably we need to modify general relativity at short distances. So this may help, modification gravity may help constructing theory of quantum gravity. Okay, one possibility is superstring theory, and another possibility may be Hodge-Lewis, and so on. Okay, and so for me, superstring is also one of modified gravity, okay, because we modify GR. Okay. And also the third motivation comes from our hope to understand GR itself. Okay, so so even if GR is the genuine description of gravity in our universe, at least at long distance, the only way to prove it is to constrain the possible deviation from GR by experiments and observation. For this purpose, I think we need kind of a prediction of modification gravity. Okay, then we can compare the prediction with the observation and experiment. Okay, and after all, I think one of the best ways to understand something may be to break it, namely in this case modify it, and then reconstruct it. So in the end, GR may be the right description, And then, but even in that case, we need to modify first. Then constrain the possible modification by observation experiments. And also even theoretically, I think it's not easy to modify gravity in a consistent way. And then we try hard to modify gravity, and then we may learn something about GR. Okay, and of course, if the modification, deviation from GR is discovered, that would be really great. Okay, so this is a third motivation. Okay, and so then there are actually many theories of gravity that modify gravity, GR, and so I think we need some criteria for good alternative theories of gravity or modified gravity. This is my personal viewpoint, and you may have different opinions, but I think many of you agree. If not, let me know later. Okay. So I think that the first of all, the theory must be consistent. Otherwise, it does not make sense, of course, to consider. And for example, we want to avoid ghost instability. And second, the theory must be experimentally viable. Otherwise, we cannot talk about mysteries. Okay, if the theory is already excluded by experiments, then we cannot talk about it. And third, it would be great if the theory is predictable. For example, if the structure of the theory is protected by symmetry, then we can make a robust prediction. That would be great. Okay. And after this introduction, I'm going to discuss so the GR itself, and including the uniqueness. And this tells us how to modify gravity. Okay, so under certain conditions, the GR is unique. So we need to break some assumptions. Okay, and then this may tell us something about the first point. So how to modify gravity and GR in a theoretically consistent way. Okay, and as for the second point, I'd like to talk about the so-called parameterized post-Newtonian formalism, PPN. And this tells us how to, this gives us a kind of a universal framework to constrain the possible deviation of GR from GR at the solar system scales. So I think this is useful for the second point. Okay. And yes, and then as for this protection protected by symmetry, this point I'd like to talk about some effective field theory approach. Okay, so this may tell us something about this. Okay. Anyway, so after these two, I'm going to discuss 3 examples, and actually these are some examples on which I have been working on. So these 3 examples will be discussed in this series of lectures. But I'm not going to talk about string theory. I mean, this is a very big subject, and also these 3 are enough for filling up my time. Okay. Anyway, so these three are covered. Okay, so the effective field theory approach. So okay, let me explain a bit about this. So this is motivated by so dark energy and dark matter. So this is IR modification gravity. Also, massive gravity is IR modification gravity. And the first motivation came from, or historically, motivation came from this very fundamental question. So can we give a mass to graviton, okay, spin to field? Okay. But nowadays, this may be considered as a source of dark energy, maybe, or dark matter. And also I'll talk about Hodge-Wiss gravity. This is a UV modification gravity and motivated by quantum gravity. Okay. So as I said, I'll cover these 3. Okay. And before ending the introduction, I'd like to, but if you have any questions about the structure of the lectures, please raise your hands. If not, okay, I'll go on. Okay. So before ending the introduction, I'd like to mention briefly about the implication of this very important event, GW 170817, on gravity theories at late time. Of course, this doesn't tell us about the gravity at early universe, but at late time, this can tell us important thing. Okay. And so we, because of this detection of gravitational waves and the simultaneous detection of gamma ray burst, we know that the speed of gravitational waves and the speed of light should be almost the same, maybe exactly the same. But we don't know. At least the difference is should be smaller than 10 to minus 15 or something like that. Okay. So this tells us many things on many theories. For example, in the so-called Hornetsky theory, which is a scalar tensor theory with second order equation motion. In this case, we have originally four free functions, G2, G3, G4, and G5. Among them, G4 and G5 are strongly constrained. Okay, G4 should be function phi only, and G5 it should be there. Okay, basically. By the way, X is I lost what the definition of X. X is a usual kinetic term, d mu phi, d mu phi. Okay, and on the other hand, still G2 and G3 are free, but recent discussions tell us that the G3 may also be constrained due to gravitational waves and dark energy interactions. Okay. And as for the so-called generalized Proca theory, which is a vector tensor theory, kind of generalization of Hornetsky theory to the vector. So because vector may have have a longitudinal part and transverse part, and the longitudinal part reduced to Hornetsky. Okay, so we have 4 free functions. On top of that, we have several other free functions, but among them, 2 functions are strongly constrained. Okay, still, other functions are free. And for this case, I'll talk about this in detail later. And the coefficient of a 3-dimensional curvature controls the speed of gravitational waves. So this is strongly constrained. Okay. So this may tell us, suggest that maybe we should find the IR fixed point with this property. And this is very important information about RG flow of this theory, probably. But yes, anyway. Then in the case of ghost condensate, I think I'll talk about this later in the section about effective field theory of tensor theory. Okay. And in this case, we don't have additional constraint, fortunately or unfortunately. In the case of massive gravity, this bound tells us that graviton mass should be smaller than this value, 10 to minus 22 electron volt. This is pretty strong, but still not as strong as the requirement from the acceleration. If we want to have acceleration by graviton mass, then the so graviton mass should be as small as something like 10 to minus 31 or 32 or something electron volt. So we need some improvement on constraint. But anyway, this constraint tells us very important information. And so I think it's now good time to think about modified gravity, because traditionally, including GR, all gravity theories have a very strong constraint from cosmological constant. Okay, so cosmological constant should be as small as 10 to minus 120. Okay, and this is really remarkably small number, and we don't have any. I mean, we don't have a solution to this. And actually, this is so difficult that the people try to forget about it. We pretend as if there is no problem like this. So at this moment, I don't have any good hope. But this is not easy. But I think not as difficult as this. So that I think it's very nice to think about this in the context of gravity theory, and tackle this. And if we can solve this problem, for example, in the context of observation gravity, then maybe after that we may have a clue to understand a cosmological constant problem. Anyway, so I wanted to say here that this event gave us a very, very good opportunity to think about alternative gravity theories. Okay. So this is the end of introduction. So if you have any questions about the introduction, please raise your hand. Probably because this is introduction, no question, but in case. Okay. at the end of each section,
yes,
stop.
someone
Yes,
raised his
please.
hand. So you can go ahead, please.
Good morning, sir.
Yes, good morning.
Thank you for your fantastic introduction.
Thank you.
I noticed the fact that you said we need to modify gravity theory at short distance in order to get the quantum gravity theory, yes. And is there any way, is there any possibility to make the contrary, meaning that otherwise we need to modify quantum field theory, quantum theory at large scale, perhaps?
You mean at short distance, right? Because the quantum gravity is at short distance. So yeah, I mean it's actually so the logical possibility to modify quantum gravity, a quantum theory at short distance. But if I have a vote, I think many people vote to modify GR. But still there is it's a logical possibility to modify quantum theory. Yes. But probably it's not so easy.
Yes, indeed, because if we put out a theory related to quantum field and general relativity, meaning that the gravity theory, quantum gravity theory, it means that this theory could explain what we observe either in small space and also in a big space, I think.
Yes. So yes. So many. Yeah. So at least I think we don't need to modify quantum theory and quantum mechanics. On the other hand, if we assume this, then I think we need to modify general relativity, at least at short distance. And also there are other motivations to modify general relativity not only at short distance, but also at long distance. Okay, thank you. So let me go on to the next section, which is general relativity and Lavrov gravity. Okay, so in order to modify general relativity, I think we need to know it. Otherwise, we don't know where we go. Okay, so in order to talk about the general relativity, I think I should start with the equivalence principle. Okay, so the first weak equivalence principle tells us this. Okay, so if we consider uncharged test body at a given initial event in space-time with initial velocity, then the subsequent trajectory is independent of internal structure and composition. If this holds, then we say that the weak equivalence principle holds. Okay, this is a definition of weak equivalence principle. And Einstein invoked more than that. So he assumed that the weak equivalence principle is valid. Also, he assumed that the outcome of any local non-gravitational test experiment is independent of the velocity of freely falling apparatus and of the time and position in the universe. Okay, so this basically tells us that the gravity is equivalent, basically equivalent to acceleration. Okay, and so if we assume these two, if these two are satisfied, we say that Einstein equivalence principle holds. Okay, and if we assume this, then this is telling us that we should have a metric. Okay, because this Einstein equivalence principle tells us that the special relativity in local free-falling frame should be valid. So there should be Minkowski metric, eta mu nu. Okay, but so the eta mu nu should be tensor. And so that if we go to the other frame, other coordinates, then the eta mu nu change values, but still eta mu nu is related to this corresponding tensor. And this is basically metric. So the Einstein equivalence principle tells us that we should have a metric. Okay, so the theory is okay. I had something, but it's not the question probably. Okay, so this tells us that we should have a metric, at least one metric. Okay, so from now on, I'm going to consider metric theory, including GR and modified gravity. But please remember that this Einstein's equivalence principle does not exclude the presence of other fields, okay, including other metrics or other fields such as scalar fields or vector fields. Okay, but at least tells us that we should have at least one metric. Okay. Okay. And so the Einstein assumed that this Einstein's equivalence principle holds these two. So that we have a metric. And also he assumed that the gravity described by the metric G mu only. Okay. The existence of this was implied by this assumption, but we don't know a priori that G mu, this metric is the only field that is responsible for gravity or not. He assumed that this is the only field that is responsible for gravity. Okay, and then this metric should be described by some invariant action. Okay, action which is invariant and coordinate transformation. Okay, change of coordinates. Okay, so this should be integral of some scalar multiplied by measure, so minus square root minus g over space-time. Okay, and this scalar should be made of this G mu nu metric and its derivative, because we assume that Einstein assumes that there are no fields other than G mu nu, so we can use only G mu nu and its derivatives. Okay, up to first derivative, we cannot construct any scalars other than constant. Okay, if we want to construct a scalar from G mu nu without derivative, then we have just contraction of G mu nu with its inverse, so which is constant. Okay, first derivative has we can construct a Christoffel symbol, but it is not a tensor, so we cannot construct a scalar out of first derivative. Up to second derivative, we can construct a scalar made of a metric and the curvature, Riemann curvature. So the ingredients in this scalar L are as follows. Okay, first constant 1, in this case 1 multiplied some coefficient, and Ricci scalar square, and Ricci tensor square, Riemann tensor square, and the derivative of scalar curvature, Ricci scalar square, and so on. Okay, there are infinite number of possibilities, but if we order them according to the number of derivatives, and we know what among them what are important. Okay, so without the derivative we have just constant. I put some scale m and dimensionless constant c0, and up to second derivative we have just the curvature, which is scalar multiplied by scale square, mass scale square multiplied by constant. Okay, dimensionless constant. Next we have a curvature square, 3 combinations, and so on. Okay, but at low energy we can forget about higher derivative terms because they are not important at long distance and long time scale. We can forget about these higher derivative terms. Then we end up with these two terms. Okay, just a constant and Ricci scalar multiplied by some constants. Okay, then if we define m Planck square and lambda in this way, then we have the standard Einstein reduction. Okay, so in this way, if we assume these two, then we naturally have Einstein theory. So with these assumptions, Einstein theory is unique at low energy. Okay. So by the way, the so-called cosmological constant problem that I briefly mentioned at the introduction, the problem of 10 to minus 120. This is basically so the question of why this combination is very, very small compared to 1. Okay. So by looking at this, you may think that this coefficient is order 1, order 1, order 1, order 1, but C0 is extremely small. Okay. So this is the famous cosmological constant problem. Anyway, we end up with
Shinji,
yes?
sorry to interrupt. There is a question by
yes,
Luis Longo. So
yep.
Ask your question.
Thanks for the opportunity. I wonder why you are truncating at the terms with two derivatives. Why you cannot go higher than that, and why you are not including cube and higher powers as well.
Right. So at this point we have infinite number of terms, and so at low energy, so from bottom up, if we increase energy scale, then these term becomes important. But once this becomes as important as this term, then all terms become important. Okay. So if we try to truncate at this point, then unless we have other reasons, for example, renormalizability, then we should include all of them. And I don't want to do that. And also, I'm interested in the gravity at long distance and long time scale compared to the so-called Planck scale. So then once we assume that this scale m is of order of Planck scale, namely the C1 is order 1, then at energy scale and the time scale, energy scale lower than m Planck, we can forget about all of them. Okay, so I throw away all of them. Okay, but you are right that there are some cases in which we can truncate at this point. For example, if we demand that theory is renormalizable, then we can truncate at this point. Okay, however, there are some problems of so-called ghost problem. Okay, so but anyway, I'm not going into details in that point at that point. Yes. Anyway, the reason is that they are suppressed at Planck scale, and at a scale lower than m Planck, we can forget about all of them. That's the answer. Does it answer your question?
Yes, it does. Thank you very much.
You're welcome. Okay, let me go on. Okay. By the way, so yes, so that maybe I should I should not spend too much time here. But so as I said, I assume that the m, so the all coefficients, dimensionless coefficients order 1, and this tells us that naturally we expect to have a order 1 coefficient here. But this is completely contradicts with our universe because of this. Okay. So this is one of the biggest mysteries in cosmology and theoretical physics. So if one of you or many of you can solve this problem, that would be really great. So anyway, so let me go on. So we now have an action like this, which is called Einstein-Hilbert action. Then we can get the field equation by taking variation. Okay, so this is the action, and then we consider variation of G mu nu metric. So by using that, so that we introduce delta G mu nu, so that we replace G mu nu by G mu nu plus delta G mu nu. Then find, for example, this square root minus G has a first variation of this form. Okay, and then this combination square root minus G times curvature has this variation. Yes. And then plugging these two into this two here and this two here, we get this. Okay. After forgetting about the boundary term. Okay. So this is this combination is total derivative. So this combination times square root minus G is written in terms of, written as a total derivative, so that we can forget about it as far as we can talk about the local equation motion. Okay. So then we have this. So this comes from this one, and this comes from variation of this times this. Okay. Now, so by adding matter and demanding that the variation of the action with respect to G mu nu vanish, we have this equation. Okay. So this is the so-called Einstein equation. Okay. I think most of you are familiar with this. Where G mu nu, this m Planck square was introduced here, but this is related to the familiar Newton's constant in this way. Okay, and by the way, T mu nu is so the stress energy tensor matter fields, which comes from the variation matter action, okay, which is defined in this way. now we know that the equation motion of general relativity. And now I'd like to count the number of degree freedom. Okay, we know that general relativity have gravitational waves. So and also the plus mode and cross mode. So they correspond. So we say that general relativity have two polarization or two degree freedom. Okay, someone has a question. Okay.
Yes, please ask.
Yes, please, sir. I don't know if I'm wrong, but it seems like the variation of the action I, which gives the integral, the last integral, perhaps it is the variation of I total or only I method. Since we see into the brackets the root of minus g times 2 over 2 times the
so
t nu nu.
We combine this, and then we demand that the sum of this and this vanish. Then from this we get this, and from this we get this. Okay, so we demand that the variation of the total action vanish.
Yes, indeed, it is the version of total action, but it seems like in the question we see only the version of the matter action, unless I'm mistaken.
Yeah, of course we demand that the matter action holds. Yes, matter equation motion holds. Yes, but this variation matter is independent of variation metric. So we separately demand that the coefficient of delta G mu nu in total variation of total action vanish, and also the coefficient of delta matter vanish. Okay. So we have Einstein equation and matter equation motion.
Thank you, sir.
Welcome. Okay, so let me go on. So we now want to count the number of degree freedom. For gravitational waves, we know we have 2 degree freedom. We want to make it completely nonlinear. Okay, so gravitational waves counting plus mode, cross mode is kind of linear perturbation. We want to go beyond this. Okay, so metric G mu nu, this is a 4x4 symmetric and non-degenerate tensor. So we have 10 components. Okay, so if we go to phase space, we introduce a momenta conjugate to these 10 components. So we have a 20-dimensional phase space at each point. Okay. Then we want to divide this 10 component into so-called laps and shift and 3D metric H mu nu, Hij. Okay. This is because we want to go to the kind of Hamiltonian formulation. Okay, Hamiltonian treats space and time separately, so that we decompose the 4-dimensional metric into 3-dimensional metric, and basically this is a 0, component of the metric and the 0i component, which is lapse shift vector. Okay, so we decompose in this way, then plug this to the Einstein-Hewitt action. Okay, so here I introduce 4 because this is 4-dimensional curvature, and I said I didn't include cosmological constant, but inclusion of cosmological constant does not change this argument. Okay, so if we do that, then this action can be written in this way. Okay, so the 4D curvature includes contribution from the 3-dimensional curvature computed from this 3-dimensional metric, which is written in this way. Okay, 3 means the 3-dimensional curvature, and also we have dependence on the time derivative of this Hij, because Hij is a dynamical field. So we want to have a kinetic term for Hij. Okay, but Hij dot is not the tensor, but this combination is 3-dimensional tensor. Okay, this is so-called extrinsic curvature, and so this is the time derivative of 3-dimensional metric, and this is a derivative of shift function, shift vector. Okay. And this is a 3-dimensional covariant derivative constructed from Hij. Okay, so this combination is 3-dimensional tensor, and this is called extrinsic curvature because this tells us how a constant time surface is embedded in space-time. Okay, so we have a square of this. So we have a Hij dot square here and here. Okay, but we don't have a lapse function dot, okay, n dot or ni dot. We have a special derivative of this, but we don't have n dot and ni dot. Okay, we don't have a time derivative of them, meaning that the momenta conjugate to lapse and shift are exactly zero, identically zero. Okay, so they are kind of algebraic equations in the phase space. So they are often called the constraints. Okay. So and also all other constraints, including themselves, are independent of lapse and shift. So they are so-called first-class constraints. Okay, let me explain this. Maybe you might have heard about this from some lectures in gauge theories, but sometimes this is a bit complicated. So I'll explain this. Okay, so the constraints, constraints are basically algebraic equations in the phase space, and they are classified into first class and second class. Okay, as you can imagine, first class is better than second class, of course. And so in the following sense, okay. So second class constraints reduces one phase space dimension. Okay, so because this is algebraic equation, if we restrict our configuration to the configuration which satisfies constraint, then the dimension of phase space is reduced. Okay. But second class reduces only one. On the other hand, first class reduces two. Okay, and moreover, the first class constraint generates a symmetry, and or also that if we have a symmetry, there is a corresponding first class constraint. And this is actually equivalent to a pair of second class constraint. Okay, 2 is 1 plus 1. So the one first class constraint is as good as 2 second class constraints. Okay. So we have okay, 1, 2, 3, 4. Okay, this is I runs from 1 to 3. So the 3 plus 1, 4 first class constraints. Also, we have more first class constraints because, as I said, first class constraints are associated with symmetry. And in general relativity, we have symmetry associated with coordinate transformation. So we can change the space-time coordinates into any new coordinates. And we have space-time so that we have 4 coordinates. So we have 4 generators of 4-dimensional diffeomorphism invariance. Okay, so we have 4 first-class constraints correspondingly. Okay, so we have 4 plus 4 first-class constraints. Okay, we started with 20-dimensional phase space. Okay, because we have 10 metric components. Okay, 20-dimensional phase space, and we have 4 plus 4 first-class constraints at each point, and each of them reduce 2 phase space dimensions. So 4 plus 4 times 2, if we reduce this, we end up with 4-dimensional physical phase space. Okay, and when we go to the phase space, we multiply by 2. So when we go back, we need to divide this by 2. We end up with 2 local physical degree freedom. Okay, so number of degree freedom in general relativity is 2. Okay, this corresponds to transverse terrestrial gravitational waves. But this argument is completely nonlinear. Okay, not only this applies not only to linear perturbation but also any nonlinear situation. Okay, so general relativity have 2 physical degree freedom at fully nonlinear level. Okay, so now we know equation of motion in general relativity and number of degrees of freedom. Now I want to say a bit more about the uniqueness. In a sense, we already learned about the uniqueness if we assume the Einstein's equivalence principle and say that if we assume that only metric is the field that is responsible for gravity, then at low energy, by expanding by doing kind of derivative expansion, at low energy general relativity is unique. That is what we have learned. Okay. So actually, Lovelock proved a very strong statement about the uniqueness. Okay, very and also mathematically rigorous. Okay, so I'd like to discuss about this now.
Sorry, before that, there was a question about what preceded. So why does a phase space reduction by second class constraint not generate a symmetry?
Yes. So this is basically the assumption, not assumption. I mean the definition of second class. Yes. Yeah. So if we have a first class, I mean symmetry, then so we can gauge fix, and so basically we can introduce gauge fixing condition. Okay. And the gauge fix theory is equivalent to the theory before gauge fixing, as far as gauge fixing is consistent. Okay. And then we have additional constraint. We still have a constraint. Okay. On top of that, we have a gauge fixing condition. So we have two constraints when we gauge fix, but that must be the same as first class. I mean original constraint. Okay. And now the after gauge fixing, we have a pair of constraints, and that actually second class. And because gauge is fixed, we don't have a symmetry. Okay. Yes. So and also basically the second class constraint is the same. Basically the part of the pair of a second class pair of constraints that we end up with after introducing gauge fixing. So because gauge is fixed, we don't have a gauge symmetry basically. In a sense, yes. This may be a bit intuitive or kind of pedagogical, but yes. Does it answer your question? Maybe no. Maybe yes.
I hope. I don't know. So the person who asked the question can answer that.
Okay. Yes. Yeah. Any other questions or it okay to go on or?
Yeah, you can go, I think.
Yes. Okay. So now let's talk about uniqueness of general relativity. Okay, in a more rigorous way. Okay. So this is a so-called Lovelock theorem, and suppose we have some tensor, okay, A mu nu, which is supposed to be equation motion for the metric G mu nu. Okay, but here just the tensor, okay, A mu nu, and assume that this is a symmetric tensor, and this is written in terms of the metric. Sorry, this is not Kij, but G mu nu, G mu nu rho, G mu nu rho sigma. Okay, and so so this tensor is written in terms of the metric and the first derivative of the metric and the second derivative of the metric. Okay, and also the covariance. I mean, so the divergence of this tensor is 0. And we assume that the space-time dimension is 4. Number of dimensions is 4. Then the Lovelock theorem tells us that this tensor A mu nu is a linear combination of Einstein tensor and the metric itself. This is nothing but the Einstein equation. Okay. So the motivation for these each assumption is as follows. So as I said, A mu nu is to be the equation motion for G mu nu, and therefore should be symmetric. But actually, later Lovelock dropped the assumption 1, so actually we don't need the symmetric assumption. Okay. But anyway, A mu nu should be tensor. Okay. And second, so equation motion depends on if equation motion depends on third or higher derivatives of the metric, then usually number of degree of freedom increase, and also the number of degree, so the extra degree of freedom typically ghost, which shows some instability. So we want to avoid this, so that we restrict the equation motion to be second order. Okay. So please wait. Wait for question until explaining this. Okay. So the third assumption is based on motivated by this. So if so there is an action such that the equation motion is derived as the variation of the action, and action is diffeomorphism invariant, then the divergence of this tensor is 0. Okay, so this theorem does not assume the existence of tensor, but motivated by this fact. Okay, So let's suppose G mu metric is has a variation, and but this variation is given by coordinate transformation. Okay, gauge transformation of the metric is given by this. This is a famous formula. Okay, and then the plugging this variation into the action, we get the first variation corresponding to this variation. Then the so this is supposed to be proportional to A mu nu. So we put A mu nu times square root of G. Sorry, I forgot the absolute value here. And because Lovelock originally considered Euclidean signature, so I changed it, but I forgot to change it, include the absolute value. Anyway, then the G mu nu, delta G mu nu is given by this. By doing the integration by part, we get this. Okay, so this should be 0 for any Guzai nu. So this combination should be 0. So if the action is invariant and diffeomorphism transformation, and then this should be 0. Okay, so by motivated by this, Lovelock assume this. Okay, of course, the fourth assumption is obvious. We are living in 4 dimensions. Okay, questions? Okay, please.
Yeah, go ahead. Okay, ask your question, please.
Just I see no reason for that, but in assumption 2, I'm used with Latin index to be only spatial index. This is not.
No, this is typo. Sorry, yes, I forgot to convert this KL to mu nu. Say rho sigma, and this is rho sigma alpha beta. Yes, this is just a typo.
Okay, thank you. Yeah,
I originally followed Lovelock. I respected Lovelock, so I use Euclidean signature and IJ. But then I decided to change it to the space-time, so mu nu, and then I forgot to change it.
Okay, yeah. Thank you.
Yeah, just a typo. Yeah. Okay. So, but actually, so this is usually what is known as Lovelock theorem. So if you ask someone, some expert about the Lovelock theorem, then usually the answer is this one. But actually, Lovelock proved much more than that. So what Lovelock so actually proved is the two theorems that I'm going to explain. Okay, so theorem 1 and theorem 2. Okay, so theorem 1 tells us that without assumption 4, just these 3 assumptions with KL converted to rho sigma, this is rho sigma alpha beta. Then without specifying number of dimensions, A mu nu is written this way. This is a bit complicated, but of course this is the same as before, but this is a generalization of this part, okay, in any dimensions, okay. And so small m is given by this, so that m minus 1 is upper limit of this sum. And so depending on n is number of dimensions, okay. So depending on whether we are in, say, 4 or 6 or 8 dimensions, or 5, 7, 9 dimensions, m is a bit different. But anyway, there is an upper limit. And so in 4 dimensions, we have just one term here, coming from here. Okay. Anyway, so this is a product of Riemann tensor, okay, and multiplied by some coefficient. Okay, coefficient is tensor, and this tensor is satisfying these 4 conditions. Okay. I'm not going to explain details of them, but I just want to say that assumption, condition C follows from B and D. Actually, so that we just need to assume A, B, D. But this is also nice symmetry, so I listed this symmetry, okay, following Lovelock. Okay, but anyway, so he found this, but theta. We don't know how we can write down how to write down tensor theta, okay, out of metric. Okay, theta is written in terms of metric without derivative. Okay, and but yet this is a bit complicated, so we don't know how to write it at this point. This moment. Okay, The second derivative of the metric is here. And theorem 2 tells us how to compute this coefficient and also the uniqueness of this coefficient. Okay. The theorem 2 is like this. So a bit of generalization of this tensor is this tensor psi. Okay. So the theta has a 2 index plus 4k indices. So the in total 4k plus 2 indices. Okay. And instead of 4k, here in theorem 2, 2p. Okay. P is integer, k is integer. So as a special case, we get this. Okay. So theorem 2 is a bit more general than what we need. Okay. Anyway, so so suppose we have a tensor like this with 2p plus 2 indices, and it satisfies the following properties: A prime, B prime, C prime, and D prime, and they are basically so these conditions with 4k replaced by 2p and theta replaced by psi. So basically theorem 2 helps us how to construct theta out of these conditions. Okay, and then the theorem 2 under these conditions tells us that the psi, this tensor, satisfies this kind of recursion relation. Okay, so this is exactly this tensor, and this is this part is this tensor, but the first two indices are contracted with the metric G rho sigma. So the number of indices is smaller by 2. Okay. And also this tensor is this tensor, but the first two indices are contracted by G metric. Okay. So the number of indices are 2p instead of 2p plus 2. Okay. And actually this tensor satisfies exactly the same condition, but instead of 2p, we have 2p minus 2. Okay, so this is kind of a recursion relation. Okay. Starting from a small p, we can construct the tensor psi for larger p. Okay, starting from small p, we can construct a psi with a larger p. Okay, so this tells us how to construct psi. In other words, in the theorem 1, we can construct theta by using this theorem. Okay, and also this tells us uniqueness of tensor theta and the uniqueness of A mu nu. Okay, so this is what Lavrov actually proved. Okay, as a corollary, we can derive what is usually known as Lavrov theorem. So that is I want to explain. Instead of explaining the proof of theorems, actually it's fun to try to understand these theorems, proof of the theorem, but I don't go into the details of the theorem proof. Okay. Then the corollary, first corollary, I want to consider n equal 2. N is number of dimensions. So in 2 dimensions, we have A mu is proportional to metric. Okay, we don't have curvature. Okay, this is trivial. Okay, because here, if we set n equal 2, then the m is 1. So m minus 1 is 0. So this term does not give us anything. We just have this. Okay, so as a corollary, a trivial corollary, in 2 dimensions, A mu nu is just proportional to the metric. Okay, so we don't have Einstein equation in 2 dimensions. If we don't have extra field, if we introduce scalar field, we have something like Einstein equation, but without extra field, we don't have Einstein equation. Okay, this is the corollary, first corollary. The second corollary, let's consider number of dimension, which is 3 or 4. Of course, this is of our interest, but let's consider n equals 3 or 4. Then m is actually if n is 3, n is odd. So here 2. Okay. So if n is 4, again m is 2. Okay. So m minus 1 is 1. So we have 1 term. Okay. And we just need to know the 1 theta. Okay. This coefficient. Okay. And in the next page, I'll explain briefly how to get the coefficient. But by using that coefficient, we end up with this. Okay. So the first term gives us Einstein tensor, and the second term, which is this one, gives us metric. Okay. So this is this statement corollary 2 for n equal 4 is what is usually known as Lovelock theorem. But Lovelock actually proved much more than that. And this is a proof of the corollary 2. And so, as I said, if n is 3 or m, 3 or 4, then m is 2. We have just one term because upper limit of the sum is m minus 1. Okay, and then let's consider theorem 2 with p equal 2. This theorem. So the p equal 2 can tell us how to construct the p equal 2 tensor. From p equal 1 tensor. So that this is theorem 2. And but we still have to compute this. This is p equal 1. So let's consider again the theorem 2 with p equal 1. And then we have this. Now this is maybe simple enough. Okay. So the theta tilde has just 2 indices, and this is symmetric, constructed from the metric. So this should be proportional to the metric. There is no other choice. If you want to know the more rigorous proof, you want to have a look at the lemma A2 of Lovelock's paper. But from intuitively it's obvious. We just have a metric, and symmetric rank 2 tensor is this one, and H is constant. By plugging this here. And then we know p equal 1 psi theta, and then by plugging this here, we get this. Then after some computation, we can get this by plugging this theta for p equal 2 to the theorem 1. We get this. This is the computation. Okay. So I think this slide will be open. So I think will be. Put on the website probably. Then we can have a look at this later if you want.
Yes, sure. The slides will be on the website. Yes.
Okay, great. Yes, so you can have a look. Okay. And so yes, so this is the corollary 2, and this is what is usually known as the Lovelock theorem. Okay. So so this Lovelock theorem tells us how to go beyond GR. Okay, because Lovelock theorem assumes that the space-time is a 4-dimensional pseudo-Riemannian geometry, and the metric is the only physical field. Okay. By the way, the theorem is at the level of equation motion. Okay. For this equation motion, we can get action, but he didn't assume the action. Okay. Anyway, then in order to modify general relativity at the level of the equation motion, we need to break these assumptions. So, namely, we need at least one of the following. Okay, we need to go beyond 4 dimensions, or we need to introduce extra degree of freedom, like a scalar field or a vector field or more metric or something like that. Okay, or we need to break some part of the diffeomorphism invariance or Lorentz invariance. Okay, or we need to go beyond the pseudo-Riemannian geometry. Okay, we need to do something like this. Okay, and let's before ending this section, let me think about this possibility, extra dimension, without changing anything else. Okay, so this is a so-called Lovelock gravity, partly based on first theorem that he proved. So this theorem, because this applies to any dimensions, and as you can see, if we increase number of dimension n, then the m increase, so number of terms increase. So we have more terms as we go up to higher dimension. Okay. So, indeed, the theorem two, also by combining theorem 2 with theorem 1, we can, in principle, compute this combination. But as I showed here, for n equals 3 and 4, this is a bit complicated. Okay, so this is kind of bottom-up approach. So we can start from the tensor with a small number of indices. Then we can go to the, from 2, 4, 6, and we can next go to 8 and so on. and we can continue in principle, but it's not so nice. I mean, it's not fast. Okay, it takes a long time to compute things. Okay, so then fortunately, Lovelock found a solution to the recursion relation in theorem 2. And the solution is given by this. And actually, the theorem 2 tells us that the solution is unique up to overall constant. So the solution is the solution. Okay. So this is the solution, actually. Okay. So solution is given by this. Okay. Again, psi is written in terms of the metric only without derivative. And indeed, it is written in terms of metric. And delta, this is so-called generalized delta, is written this way. So determinant of some matrix made of chronological delta. And M is the same as before. And this large D is given by this. So this is just a chronological delta. Okay. So I think it's not so complicated to show that this is a solution, but finding a solution is not so easy. But once we have a solution, it's relatively easy to show that it is a solution. And theorem 2 implies that this is a unique. This is the solution, okay, up to overall coefficient, which we call BK. Okay. Now, by plugging this to the theorem 1, here we can compute this combination. Okay, and that is given by this. Okay, and so in this way, Lovelock established the third theorem. Okay, third theorem tells us that if A mu nu satisfies condition 1 to 3 without condition 4 about number of dimensions, then A mu is given by this. Okay, just the products of the Riemann tensor multiplied by this combination. This is the generalized delta function, generalized delta with arbitrary coefficient AK, okay, plus cosmological constant term, which is just a metric. Also, he also found an action whose equation motion is this one, and it is given by this. Okay. And he, again, I'd like to stress here that Lovelock did not assume the existence of the action. Okay. So it's not obvious whether this equation, a priori, it's not obvious whether this equation motion has an action. But fortunately, it does. Okay. In other words, if we have an arbitrary equation motion, then in general, we cannot hope to find the action because we need to satisfy certain integrability condition. And fortunately, this satisfies the integrability condition, and we have action. Okay. And anyway, the theory that is described by this action and equation motion is called Lovelock gravity for obvious reason. Okay. Lovelock found it. Okay. And first two terms in here, Einstein-Hilbert action, Einstein-Hilbert term, and a so-called Gauss-Bonnet term. But the rest of them are called Lovelock term, except for this cosmological constant term. Okay, this is the cosmological constant term. Okay, so that's the end of this section. So I want to accept some questions if you have.
Yes, there is one question.
Yes, please.
Hello.
Yes.
Yeah. Okay. So I'm asking about breaking Lovelock conditions. So can we have a modified theory of gravity without breaking these assumptions? And I'm mentioning the example of the new theory for the Gauss-Bonnet gravity of Glavin and Lee.
No,
and I think that he wrote
there's no exception. Okay. Actually,
okay.
Yes, so if we have yes, so if we have modified gravity, we need to break some of them. Yes, yeah. So actually, yes, I worked on this for the Einstein Gauss Bonnet, and the only way to have for the Einstein, for the Einstein gas bond with a 2-degree freedom is this one. We need to break time difference, and we can find the theory with 2-degree freedom. But either or we need to introduce extra degree freedom. But in the case of for the Einstein Gauss bond, if we choose this one, then the extra degree freedom is kind of strongly coupled, infinitely strongly coupled, so the theory doesn't make sense. So that as far as I know, the only consistent for the Einstein Gauss bond is based on this violation. And because this is a theorem, we need to break assumption.
Okay, I think there are questions in the chat. Do these theories reduce in some way to 4D?
So, let me see.
The last, yeah.
Yes, I can see.
Can you see it?
Okay, so why does the phase space reduction by second plus constraint not generate a symmetry? Yes, so this is why I think I answered this. Yes, you already answered. Second one, do these theories reduce in some way to 4D? G compactified. Yes, okay. So that you're talking about this Lovelock theory. Okay. So if we consider for the Lovelock theory, higher dimensional theory, Lovelock, and compactify extra dimensions, we end up with a theory with extra degree freedom. Okay. And so say size of extra dimension and the shape of extra dimension, scalar fields in 4 dimensions. And also that we have off-diagonal components. So the metric has 2 indices. Components that has 1 index in 4 dimension, the other index in extra dimension can be considered a kind of gauge fields. Okay, so we have not only the 4D metric but also other fields. Okay, in 4 dimension after compactification. And so this is the same also in higher dimensional general relativity. But if we start with the Lovelock gravity, then we end up with the kind of special case of Horndeski theory. If we restrict to the 1 scalar part, okay, side of extra dimension. But we have more complicated things like shape of extra dimension and also gauge fields. And also we have a so-called Karzai modes, massive fields. So we have a lot of extra degree freedom in 4 dimensions. Yes. So this is related to this actually. If we go to higher dimension, then compactify, then we end up with the extra degree freedom. Yes. I hope this answers the question. If not, please raise the hand. Shall I move on to the next part?
Yeah, there is another question in the n equal 2 corollary 1. There is no Einstein tensor. What is the consequence in geometry of the space?
Yes. So we just don't know how to fix the metric. That's all. Okay. We can have some non-trivial geometry. Okay, you're talking about this one. Okay, yes. So we don't have some equations that can tell us how to fix the metric. That's all. Okay, but we can consider non-trivial geometry by hand, and on top of that, we can consider say scalar fields, quantum field theory in curved space-time in 2 dimensions, and so on. And or we can introduce extra field. Okay, for example, if we start from the 4 dimensions and compactify 2 dimensions, then we end up with, or we can consider spherical symmetric reduction. Then the area radius can be considered as a scalar field in 2 dimensions. And then we have the so-called Dilaton kind of special case of Dilaton gravity. So we have not only the metric, but also scalar field in 2 dimensions. In that case, we have a field equation for the metric. No, for the scalar field, okay? And also the metric. But if we have just a metric in 2 dimension, we don't have equation. Is there the question?
Yeah, there is. Okay, and I think there is no
Someone
more
is raising
comment about
hand.
it, but there is another question
Yes.
on the other hand. So,
yeah, in the action of the theorem 3 slide.
This one? Yes.
Yeah, so these coefficients AK, is there any general expression for them? Or you just constrain them? Yeah.
Ah, yes, this is given by this. This is a closed form expression.
No, I
so
mean
the
the AK, not the delta one.
Ah, AK is arbitrary coefficient. Yeah, this is just a constant. So the for example, in the case of general relativity in 4 dimension, this is arbitrary constant. This is arbitrary constant, right? Where? Okay, yes. So
they're not fixed at all.
Planck scale and the cosmological constant, but they're just constants. Yes, arbitrary constant.
Okay. Okay. Thank you.
Yep. No waiting. Okay. Other questions? No.
I don't think so.
Yes. So do we have to take a break or
as you wish? If you are on time, we can have a short break. Otherwise, you can go ahead.
Okay, so maybe I can go ahead. I mean, because we already have some questions. Okay.
Okay.
So, yep. So let's move on to the next section, which is about parameterized post-Newtonian formalism. Okay. So as we know, I mean, so there are many modified gravity theories and also many gravity experiments. Okay. And of course, we can constrain each theory by each experiment, but the combination of number of experiments and theories are a lot. So it would be nice if we have some universal framework that can summarize the results of experiments and that can universally constrain theories, set of theories. Okay. So that is parameterized post-Newtonian formalism or PPN formalism. This is very, very useful. So I want to explain this. Okay. So formalism is as follows. So we start with the stress energy tensor. Okay, we consider so gravity produced by matter, of course, and the matter in this formalism is usually considered as perfect fluid. Okay, perfect fluid is is represented by stress energy tensor, which is isotropic in its rest frame. Okay, so this stress energy tensor is characterized by 3 velocity and rest mass density and isotopic pressure, because the perfect fluid by definition is isotopic. So we don't have anisotropic stress, but we have just isotopic pressure. And also we introduce a specific energy density. Okay. And then we can construct 4 velocity out of 3 velocity in this way. Okay. So spatial component is 3D velocity multiplied by some factor, and same factor goes here. Okay, and this U0 is determined by this normalization condition. Okay, U mu is supposed to have a unit norm. Okay, and rho and rest mass density, I divided the total energy density into rest mass energy density plus specific energy density. And the reason is that this part satisfies the kind of conservation equation, okay? Baryon number conservation, okay? So the energy density, rest mass density multiplied by 4 velocity has a vanishing divergence, okay? Also, the T mu unit should have a vanishing divergence, okay? as we have seen already. So as far as matter action is invariant under diffeomorphism, T mu nu is a divergence of T mu is 0. Okay, so so these three equations, a set of equations, are basic equation for stress resistance. Then we introduce the so-called post-Newtonian bookkeeping. Okay, so we consider free velocity as small quantity. So we introduce epsilon, and so this velocity is basically the dx over dt. Okay, so the time over time is denominator, and x space component spatial coordinate is in the numerator, which is epsilon. So this means that the time derivative should be order epsilon higher than the spatial derivative. Okay. Also, we consider the kind of potential to be epsilon square. Okay, because if we consider kind of bound system, then the velocity square should be balanced by gravity. Sorry, this is not so that yes, this is the yeah, okay, it's a force or potential. Yes. This is the potential. Yes, sorry. So this is energy density, and small L is the size of the object, and capital L is the distance between the object, matter source, source of the gravity, and the object that we observe. Okay, we have something like this, and we observe this one, and this is small L is the size of the source of gravity. Okay. And also, pressure is higher in epsilon, this is the assumption, and specific energy density is also higher. Okay. In this, with respect to this post-Newtonian bookkeeping, this is their assumption. Then so before going to the post-Newtonian, we need to specify Newtonian metric, which is given by this. So the only non-trivial part is a 0,0 component, which is Newton's potential. Okay, so if we consider theory which is not GR, then this fact that the G Newton here is not trivial thing. Okay, so actually we define Newton's constant by this equation. Okay, so we'll see later in some example. Okay, so in GR, automatically we have this, but in other theories, we compute G Newton by this. Okay, so we define G Newton in such a way that G0 component is of this form. Okay. Now, let's move on to the formalism. So we need to consider higher order correction with respect to epsilon. Okay, so this is Newtonian. So we go to the post-Newtonian. So this is order 0, epsilon square. This part is order epsilon to 4. Okay, and this is epsilon cube. Okay, this part, and we also need to introduce epsilon square part here. Okay, this is this one. Okay, and perhaps you can have a look at these definitions later on my slides, which will be on the website of the conference. Okay. So, but anyway, so we have many potentials, and so usually in textbook, like with textbook, they are written in the integral form like this. But the conversion from integral form to the differential form is straightforward. And for actual computation, at least for me, it was easy to use this differential form by using Maple or Mathematica. It's very easy to compute PPN parameters in, say, scalar tensor theories. Okay, so for this reason, I wrote down the integral, differential form of the definition of, say, a potential U is defined by this, and X is defined by this, and so on. Okay, and then each potential has a coefficient parameterized by this actually 10 plus 1 parameters. Okay. These red ones are standard 10 ppn parameters. But if we want to consider theory with broken time differ, then we need one more. Okay. So for example, if we want to consider something like for the Einstein-Gauss-Bonnet or whatever, or say Hodge-Blix gravity, then we need additional ppn parameters, sort of ppn parameters. Okay. And then here I already fixed the spatial choice of the spatial coordinates, but the time difference is not fixed. Okay. So the residual gauge freedom is generated by time difference. So the time component, zero component of Guzai mu, which can be parameterized by this potential x, where x is defined by this. Then the spatial component is said to be 0 and lambda is constant. Then the matrix transform in this way. So if we consider theory with the 4D differential invariance, like a GR or usual scalar tensor theories, we can use this to simplify the PPN, this PPN metric. This form of the metric is called PPN metric. Okay. So by looking at this, so this lambda enters in this convention, phi 6 b, carry b, and phi 1, or phi 6 here, and phi 1 and carry b, all include theta b. So actually by using this, also the spatial time component has this one, and they all together can be cancelled by setting lambda to minus theta b divided by 2. Okay. So in theory with 4D differential, we can set the theta b equal to 0, but in general we cannot. Okay. So we have 10 standard PPN parameters which are observable, plus one additional kind of PPN parameter. Okay. But actually this is unobservable if the matter sector has 4D differential invariance. Okay. Even if the gravity sector does not. Okay. Because gravity is probed by matter, motion of say planet or whatever. And so if matter does not feel the effect of this guy, then this is unobservable. Okay. So, however, in order to compute these 10 components or 10 parameters, we need to introduce this. Okay. After computation of these 10 parameters, we can forget about this, but for the computation, we need it. Okay. By the way, GR has these values. Okay. Gamma equal 1, beta equal 1, and all others are 0. And the theta b is gauge freedom, so we can set it to any value, say 0. Okay. So only gamma and beta are 1, all others are 0. Okay. So solar system experiments can constrain the deviation from these values. Okay. So deviation gamma from 1 is constrained by various time delay and light deflection and so on, up to say 10 to minus 5 or something. And gamma minus 1, so beta minus 1 is also constrained in this way. And the Guzai and other variables, PPN parameters are constrained in this way. Also, there is some additional constraints coming from strong gravity regime, okay, like pulsars. Okay, and but this is beyond the assumption of PPN parameterized post-Newton expansion. So rigorously speaking, they are not PPN parameters, but this is a kind of strong gravity extension or generalization of PPN parameters. So they are usually sometimes denoted as say Guzai hat, alpha 1 hat, and so on. But this is a strong gravity version of alpha 1. And as a result, we have different constraints. Okay. So if we want to consider some theory beyond the general relativity, we need to take into account these constraints. Okay. And once we have a table of constraints, and each theory should satisfy these constraints. And so it would be nice if you have a dictionary between theory parameters and PPN parameters. So if you have some favorite theory, we can compute PPN parameters. Then look at this table. you can say whether your favorite theory is allowed or excluded. Okay. So let's consider a simple scalar tensor theory as an example. And I show you the kind of sketch of computation of PPN parameters. Okay. So that after going home, you can compute the PPN parameter of your favorite theories by yourself. Okay. So in scalar tensor theory, in this simple one, we consider metric and the scalar field as basic variables. And of course, we introduce matter. Okay. And the matter is represented by stress energy tensor. And action of scalar tensor theory is written in this way. So the gravity part and the matter part. And the matter part also matter couples to metric G mu nu. And the G mu nu and the phi are described by this action. Okay. So the previously in general relativity, we had Einstein reduction. So the scalar Einstein rich scalar is just was multiplied by just constant, but now it is multiplied by scalar field. Okay, that's why it is called scalar tensor theory. And also we have a kinetic term of scalar field, which is a first derivative square, and multiplied by some function phi. Okay, this is action, and we have equation motion for phi in this way, and the scalar field is sourced by trace of stress energy tensor. Okay. And the equation motion for the metric, in other words, the Einstein equation, kind of modified Einstein equation of this form. Okay. Then we consider PPN expansion. So the G mu nu metric is like this. So that we consider this PPN metric, but we can set the theta b to be 0 because we have 4D differ. We can use the time differ to set theta b to be 0. Okay. And also we need to solve the equation of motion, say especially this equation motion for phi with respect to scalar field. And so we need to also expand scalar field in this way. So okay, there's order in epsilon, second order in epsilon, fourth order in epsilon, and higher order. And we expand each part by potentials that I introduced here. Okay. Similar to this expansion. Okay. We consider these coefficients as free, some constant, okay, that are determined by equations of motion. Okay. Then we of course consider T mu nu as a perfect fluid form, as in the standard PPN. Then we have 10 PPN parameters and Newton's constant. So Newton's constant here is a derived quantity, not a given quantity. Okay, and also a lot of unobservable parameters. I mean, gamma, phi, and UCC, and so on. They are unobservable constant parameters because matter couples to the metric. So as far as we know matter, we can compute the motion of, as far as we know the metric G mu nu, we can compute the motion of matter. So they are observable, but we need them to compute observable quantities. Okay. Now we can compute so by BPN parameters by several steps. The first step, we can compute the equation motion for phi up to at the second order in epsilon, and also the zero component of Einstein equation up to, at the second order in epsilon. Then they can be solved with respect to G Newton and gamma phi. Gamma phi is the coefficient of this. Unobservable, but we need to determine this to go to the next step. Okay. Then the G Newton is given by this. And in the second step, we consider trace of the spatial part of the Einstein equation of this order. We can compute gamma. This is observable quantity. Okay. Then the off-diagonal component of the Einstein equation tells us that alpha 1 is 0. And then we can compute the fourth order part of the equation motion for phi. They have, I think, 8 independent terms, so that we set each coefficient to be 0. each coefficient to be satisfied, then we end up with those results for the coefficients of these potentials. Okay. We also need them to go on to the next step, but they are unusable. Then the final step, the fourth order of the zero component, we have again 1, 2, 3, 4, 5, 6, 7, 8 independent terms. So we have 8 equations. They are solved in this way. Okay, beta this is observable, but still not convenient form. And then the other PPN parameters are said to be shown to be 0. Okay, now beta can be simplified by setting G Newton to 1 by choice of unit. Beta is given by this. Without doing this, we have this formula. I think this is what is usual formula that is well known. But before that, if we don't set this, we have this actually. Yes. Okay, so let me summarize PP. So I think you can follow these steps and do the same thing for your favorite theories to compute PPN parameters and to see if your theory is consistent or not with the experiments. Okay, so let me summarize PPN formalism. We can go beyond GR, but only to the extent that it is consistent with all experimental constraints. Okay, there are many theories and many experiments, but thanks to PPN formalism, possible deviations from GR at the solar system scale are universally constrained by experiments. Okay, so we have 10 PPN parameters and G Newton. They are calculable from theories, and they are constrained by solar system scale experiments. Okay, so by computation from theory and constraints, we can constrain the parameters in the theory. Okay, and so I showed a table of constraints on the PPN parameters, and I showed how to compute PPN parameters in scalar tensor theory as simple example. Okay. So we can do the similar computations in your favorite theories. Okay. So I want to see if there is any questions or not.
Yes, there is a question
yes,
by
please.
Luciano Rezzola.
Okay, sorry. I didn't know.
Thank you for the very nice presentation. I have a question about the constraints from observations. All of the ones you mentioned are, weak field.
These are weak field, yes, but they are strong field.
So the question is, does it make sense to set strong field constraints from, say, black hole observations?
No, no. So we need to compute from scratch these strong gravity version of kind of strong gravity extension of the PPN parameters from the theory from scratch. So the given theory, the same theory can give us different value of Xi and Xi hat, actually, and the different value of alpha 1 and alpha 1 hat. And the computation of these values are not so simple, actually.
So are there any, are there any expressions where people can, just use constraints from strong field observations? I'm thinking about quasi-normal modes of black holes or, shadow radius, and from this set constraints on a PPN parameters, or it simply doesn't make sense?
I think, as I said, computations of these parameters from given theory is in general very complicated, and we need to compute the so-called, for example, sensitivity, and that involves nonlinear computation. And say it depends on also the equation state and many complicated things. But in principle, if we have some favorite theory, then we can compute, and I think we can compute this this strong field version, a strong gravity version of PPN parameters from the theory parameters, and also the probability equation state, and so on. Okay. Then we can constrain. Yeah.
Okay.
But they are weak field, and we can simply apply them to the PPN parameters. I mean PPN parameters computed in this way. So be careful about this distinction.
Yeah. Okay.
This is a very important point.
Thank you.
You're welcome.
Okay, I think there is no more question.
Yes.
So you can maybe continue, carry on.
Yes, which one? So
I think there is a comment, but there is no.
Okay,
no
yes.
question.
Yeah, thank you for the comment. Yes. So there is a paper of PPM parameters constrained by the shadow from the event horizon telescope. Yes. Yep. Thank you. But it's important to distinguish these two constraints. Yeah, sometimes these constraints are put together in the same one table, and then sometimes it's very confusing. Yes. I hope I didn't make a mistake. Okay, so any other questions? If not, let me move on to, no, it's, I still have, yes, okay. Yes. Is it okay to move on to the next section?
I think so.
Great, yes. So let's move on to the next section, which is about effective field theory of scalar tensor theory. Okay, so as I said, I mean, and as you know, there are many modified gravity theories, and zoo of modified gravity theories. And so I think we need to know some checkpoints. Okay, so once we are given some theory, which point we should think. So first, I think we need to know what are the physical degree of freedom in the theory, and we need to know how they interact. Okay, so given, I mean, so say some theory has say two polarization of gravitational waves and the scalar field, and then we need to know how they interact. Okay, and also that we want to know the regime of validity of the theories. Okay, some theory is good only at low energy. Some theory may be good all the way up to Planck scale or maybe above, and if the theory is UV complete, like a string theory or maybe Hodge gravity. But usually there is a so-called cutoff scale above which we cannot trust the theory. So we need to know the regime of validity of the theory. Okay, and if two or more theories give the same answers to these three questions, then I think they should be the same, okay, even if they look different. Okay, so this suggests that there should be some universal description. Okay, so this is so the reason why I want to talk about the so-called effective field theories, but specialized to the so-called scalar tensor theories. Okay, so scalar tensor theories, as we have already seen a bit, is described by a metric and a scalar field. Okay, so this satisfies the Einstein's equivalence principle, and this is a metric theory. But as I said, Einstein's equivalence principle does not exclude the possibility of including extra fields, okay, such as scalar field. Here we consider metric and the scalar field. Okay, and the scalar tensor theories were considered by many people, starting with Jordan, Brown-Stieke, Bergman, Wagner, and so on. And most general scalar tensor theory with second order equation motion, which is covariant, was constructed by Horndeski in 1974. And recently, more general theories, so-called DOST, beyond Horndeski, were constructed by David and Karim in 2016. And this is very general and very nice. And actually, so that all of them can be described by effective field theory, okay? At least at low energy. Not high energy, but at least at low energy, we can universally describe all of them. Okay? This is the strength of the effective field theory. Okay. Some theories may be applicable to at high energy. This EFT applies only at low energy, but this is completely universal. Okay. So especially here, I'd like to consider a situation where time diffeomorphism invariance is broken by the background. For example, during inflation. So inflation is, as we know, the accelerated expansion of the universe in the early universe. Okay, and but the inflation should end. Okay, otherwise the universe expands exponentially all the time, and then the universe would be empty. We cannot accommodate the universe like what we are living in. Okay, so the inflation should end. So the exponential expansion should end at some point. Okay, and in order to do that at almost the same time, okay, we need to do that almost the same time. Otherwise, I mean the exponential expansion ends here earlier, and exponential expansion here later. And so it's completely chaos, and so universe after that would be completely inhomogeneous. So we want to end the exponential expansion almost at the same time. So in order to do that, we need to have some field that can tell us the time that is remaining before the end of this exponential expansion. Okay. Otherwise, this part of the universe and this part of the universe don't know when to end. Okay. So if we prepare some field, then we can end this exponential expansion almost same time. Okay. And the simplest case is a scalar field, because we need to record the time remaining, which is one number. So the field that can store one number is the scalar field. So the scalar field is the simplest case for responsible for the timekeeper. Okay, and this should have a non-vanishing derivative. Actually, it is time-like because we need to end. So this means that the value of a scalar field should change as we go from past to future. So the derivative should be time-like. Okay, so this means that during inflation, whatever it is, time difference should be broken. Okay, by the background. The underlying theory can be covariant, but by the background, time difference should be broken, at least during inflation. Okay, and however, we want to keep special difference because partly because we want to have almost homogeneous and isotropic universe. And so this is a symmetric break, kind of pattern of symmetry breaking. Okay, so we want to keep this pattern. Okay, and then with this symmetry breaking pattern, we need to include all terms that respect this remaining symmetry, namely the spatial difference. We need to include all of them in the effective field theory action. Okay, then as I said, this EFT effective field theory valid only at low energy, but at low energy, this is completely universal. In order to do that, we just need to do derivative expansion. Okay, at low energy, derivative is small, so that we can expand the action by number of derivatives. Okay, this is what we do, and also we do expansion with respect to perturbation around homogeneous isotropic universe. Okay, and if the universe is almost homogeneous and isotropic, this expansion with respect to perturbation makes sense also. Okay, so this is what we do. Then after doing that, we truncate at some finite number of terms. Then we can, if we want, we can recover diffeomorphism, because diffeomorphism is a kind of gauge symmetry, and gauge symmetry is just a redundancy of description. Okay, same different configuration represent the same physics. This is nothing but redundancy, and gauge symmetry, all gauge symmetries are just a redundancy. So diffeo is also gauge symmetry. So by introducing redundant degree of freedom, we can recover diffeo. Okay, so this corresponds to Nambu-Gosson boson, or in this case we end up. So this Nambu-Gosson boson corresponds to, in the case of inflation, the fluctuation of inflaton. Okay. And in the case of dark energy, this number Goldstone boson corresponds to dark energy, fluctuation of dark energy. Okay, so following this procedure, we can construct the effective field theory of scalar tensor theory very universally. Okay, and the simplest one is the so-called ghost condensate, which I developed some years ago. So I want to explain this, then generalize to more general case, including inflation. Okay. So the ghost condensate is kind of analog of Higgs mechanism. As you can see from this sentence, we specify the kind of pattern of symmetry breaking. Okay. But if you hear some word like symmetry breaking, of course you remember Higgs mechanism. Okay, so the ghost condensate is exactly the analog of Higgs mechanism in gravity. Okay, so in Higgs mechanism we consider potential like this. Okay, so we have instability here, so-called tachyon, and but we have nice minima here, where first derivative is 0, but the second derivative is positive. Okay, so the scalar field can condense here or here. Okay, and in the case of ghost condensate, instead of the wave of scalar field, we consider wave. Wave means the vacuum expectation value. Okay, some value. I mean background value. Okay, background value of derivative of scalar field is a kind of order parameter of symmetry breaking. Okay. How much symmetry is broken is measured by this value. Okay, and in order to give a non-vanishing value to this combination, we consider nonlinear kinetic term. Okay, so this is I mean d phi square is a usual kinetic term, but we can consider nonlinear kinetic term. For the homogeneous case, this is a function of phi dot. Okay, dot is time derivative, and let's consider this kind of shape, like Higgs potential. Then actually this part is unstable, so we cannot live there. But we can live here and here, where first derivative is 0 and second derivative is positive. Okay, so in the case of Higgs mechanism, so this field is charged under gauge symmetry. So the gauge symmetry is broken spontaneously, and the gauge force is modified. Okay, similarly in the ghost condensate, the scalar field, derivative scalar field gets expectation value here. As a result, time translational symmetry is broken spontaneously and gravity is modified. Okay, this is the basic idea. And but without talking about this kind of nonlinear kinetic term, we can universally construct, systematically construct the low energy effective field theory. Okay, so this is what I want to do. Okay, so this is basically a review of this paper, part of this paper. So so if you are interested in it, you can have a look at this. Okay. And but I hope you can my explanation is simple enough so that you can understand from this lecture. Okay, and let's consider background characterized by non-vanishing expectation value of derivative scalar field, and we assume that this is time-like, because as I said, for example, there are inflation or derivative phi is time-like. Okay, so this is the assumption. Also, that we don't want to break spatial diffusion. Okay, and rotational symmetry. Our universe is almost homogeneous isotropic, so we don't want to break it. So we assume this, and then also we assume that the metric background metric is maximally symmetric, either Minkowski or Dojita. Okay, so Dojita may be considered as a simple description of inflation or late time acceleration, and Minkowski may be local universe. Okay, and later I will explain generalize this to Friedman background. Okay, so with these two assumptions, we can just get this effective field theory action. So I'd like to explain how we can get this action universally. Okay, so because of first assumption, okay, d mu phi is non-zero and time-like, we can actually choose a coordinate, in particular time coordinate, so that scalar field agree with time, or we can just choose time as a scalar field. Okay, So given configuration phi, we can introduce new time coordinate by just phi. Okay. Then this means that the fluctuation of scalar field, which we sometimes called pi, is 0. This is a gauge choice. Okay. And then with this choice, the residual symmetry is spatial differential. Okay. This is spatial coordinates can be changed to any function of time and space, as I wrote here. So the spatial differential is unbroken. Okay. So this is unbroken symmetry. So we can write down most general action invariant under this residual symmetry. Okay, this is this strategy. Okay, we need to include all terms that respect the spatial differential. Okay. Later, if you want, we can introduce scalar field perturbation pi by undoing this unitary gauge. Okay, I will explain this also later. But let's first consider this step. We can write down most general action invariant under this residual symmetry. Okay, we know that metric perturbation h mu nu and Minkowski metric is transforming like this, and space-time diffeomorphism transformation. Xi mu is for vector. Okay, and this residual symmetry is generated by this spatial component. Okay, so we just consider Xi I, but we set Xi 0 to be 0. So the H00 transform to the original metric. So the H00 does not transform, because if we set 0, 0, 0, 0 here, but the Xi 0 is 0, so this is 0. Okay, so this is invariant. And the H0 component change like this: 0i, I0, and I0, this 0. So we have just one term. Ij component transform like this. Both contribute. Okay. So now H00 is invariant, so we can use H00 in the action. Okay. But we need to consider H0 square, because we assume that the background metric is Minkowski. Here, for simplicity, we consider Minkowski. Generalization to Dojita is simple, so that for simplicity, let's consider Minkowski. And then if we have a term which is linear in perturbation, this gives us a non-trivial equation motion, meaning that Minkowski is not a solution. Okay, and so the action should start from second order, quadratic order. So that's why I consider H0 square. But we cannot use H0i square, because H0i is not invariant under spatial differential. But by looking at these two formulas, you can see that if you take a spatial derivative of this and time derivative of this, by combining them, we can construct an invariant combination, which is this. Okay, time derivative of spatial space component and spatial derivative of the time space component symmetrized. If we take a difference, this is invariant. Okay, so we can use this combination in the action, of course, and this is nothing but the extrinsic curvature that we have seen in the Hamiltonian analysis of general relativity. So this represents how constant time surface is embedded in space-time. That's why this is invariant. Actually, in general, this is a spatial tensor, and because the background value of this is 0, the Kij, which appears at the linear order, is invariant. Okay, so we can use this, and but we need to square it. Okay, so we can consider a square of trace and trace of square. Okay, they are independent. So in the action, we can consider H00 square and trace square and the Kij, trace of square. On top of that, of course, we need to consider Einstein-Hilbert action, because Einstein-Hilbert action is invariant and 4-dimensional differential, which includes 3D differential as a special case. So we also should include this. Okay, but anyway, these are universal terms. Okay. Now, of course, we can consider infinite number of terms as in our first derivation of Einstein-Hilbert action. We had a bunch of terms which is nonlinear in curvature and derivatives and so on. We have this or similar structure here. Okay, So we can, for example, we can consider say H0 to 4 and H0 to 6, or extrinsic curvature to 4 or something like that. But actually they are suppressed at low energy, as I will show later. Okay. Anyway, so let's consider these 3 terms plus Einstein reduction. Then the action for pi can be recovered by undoing this unitary gauge. Okay. So we fix this and consider the spatial diffeo as a residual symmetry, and we can undo this gauge by introducing Gzai 0. So we can promote Gzai 0 to a physical field pi. Okay. Then consider this transformation. Okay. Then we see that H00 transform like this. Okay. Because Gzai 0 upstairs is pi, so the Gzai 0 downstairs is minus pi. And then the, here, okay, H00 transform like, so this Gzai 0 downstairs is minus pi. This Gzai 0 downstairs is minus pi. So we have 2 terms, therefore we have this, okay? And also it's easy to show that the Kij defined in this way transform like this. So by plugging this to here, we get this. By plugging this to here and here, we get this and this. This is how we got this, this action. Very simple and universal. We cannot change here anything. This is completely universal. As far as symmetry breaking pattern is the same, you get this. Okay, of course, the value of coefficient alpha 1 may be different, alpha 2 may be different, and m may be different, but the structure is the same. Okay. By the way, by plugging this to here, we don't get anything. We have the same Einstein reduction because Einstein reduction is invariant under 4D diffeo. Okay, invariant by this. Okay. Now I want to show that the terms that in principle be there can be ignored at low energy. This is very important because in general you have infinite number of terms. We don't know which one is important. Okay, we want to show that they are unimportant at low energy. Okay, this is what I do now. Okay, in order to do that, it's convenient to take the so-called decoupling limit, where we consider only a fluctuation of scalar field, namely pi, but we ignore the perturbation of metric. Okay, so this can be justified under certain condition, but I'm not going to explain this. But let's consider only a part that depends on scalar field pi. Okay, then from this part we get pi dot square. If we set h0 square h0 to be 0, we get just a pi dot square. After normalizing pi and redefining m, we get pi dot square. Okay, and also from here and here, if we set the metric perturbation to be 0, so namely that this is 0, then we get a second derivative pi squared, and here also second derivative pi squared, and they are in principle different, but by doing integration by part, both of them are of this form. Okay, so we have these 2 terms from these 3 terms, and we don't get anything from here because this term doesn't include pi. Okay, so now we want to see how the fluctuation, especially quantum fluctuation of pi, scales as we change energy scale. So this, in order to do that, the so-called scaling analysis is very convenient. So let's consider a change. Let's change given energy scale E to E times some number R. R is some number. Okay, we scale energy scale, and of course, because of the famous relation between energy and time should go like this. Okay, coefficient should be inverse of this coefficient, and so dx spatial change. I mean the value. So the difference of the infinitesimal difference of the spatial coordinates should scale like this, because as you see from here, we need to balance these 2, and the pi, we have 2 pi's, pi square, but here 2 time derivative, here 4 spatial derivatives. And we want to make them to balance with each other in order to estimate the amplitude of quantum fluctuation. Okay, so square of spatial derivative is the same as 1 time derivative. So the spatial dx should be square root of dt. So we have this number, -1/2 instead of -1 here. Okay, and then by plugging these 2 scaling to this action 2 terms, including this integration with respect to time and spatial coordinates, we see that the pi should scale like this in order to make this action to be invariant by scaling. Okay, so from dt we get -1. The 3 from volume we get the 3 factor of this, and the 2 time derivative give us so the 2 factor of r, so the -2 factor of this factor. Okay, and then we have some factor of so suppose this is s, r to s, we have 2s, and then they must be invariant. So then s is determined to be 1/4. Okay, so this is not 1. Okay, in usual scalar field theory, the scalar field scales like energy, but here scales like 1/4 of 1/4. Okay, scaling dimension of this is said to be scaling dimension 1/4. Okay, so by these scaling dimension, we can estimate the leading nonlinear operators that are present here. Okay, which is this one, for example. Okay, then you can compute after this lecture, perhaps because I don't have time to count. Maybe I can do, but maybe I'll skip. Okay, anyway, you can do that. Okay, by using this scaling, and then this turns out to have a scaling dimension 1/4. Okay, so as we change energy scale, say by reducing energy scale from high energy to low energy, then the importance of this term becomes smaller and smaller. So that this term scales like energy to 1/4. Okay, the power is this one. Okay, and on the other hand, these 2 terms do not change because they are invariant under this scaling. Okay, so as we go down to low energy, this is completely negligible. If we go to the very low energy, so that we can consider these operators, for example, this one as a correction to these 2. We can do the same thing for any other operators here, show that they have positive scaling dimension. So at low energy, they are not important. Okay. So the reason why I wrote here barely is that this is not 1, not integer. So the separation is weaker, but still suppressed. So it's good. Okay. So at low energy, we have a good control of these terms, and we have good low energy effective field theory. We can make a robust prediction. Okay, so for example, if we apply this kind of effective field theory to inflation, we can construct ghost inflation, for example, okay, but also other type of inflation. If we generalize this EFT, okay, so which is the subject of next slide. Okay, so this effective field theory can be this effective field theory was constructed in Minkowski or Dojita background, maximally symmetric background. So the ghost condensate is a universal effective field theory of scalar tensor theory in Minkowski and the Dojita background. Okay. But in more general Friedman, Robertson-Walker, Robertson-Walker background, we need to extend. And actually, this was already done by these smart people. And this is now known as the effective field theory of inflation. And in the case of dark energy and late time universe, this is known as effective field theory of dark energy. And actually, this EFT of inflation was adopted by Planck team and used to constrain non-Gaussianity. I will touch on that very briefly later. Okay, so the construction of this EFT of inflation or dark energy is basically the same. Okay, so we just construct the action which is invariant under spatial diffuse. Okay, as we go back, we had this strategy. So all terms, we need to include all terms that respect spatial diffuse. Okay, the same here. We included all terms, and we do the same thing here. Okay, and But we need to do a bit more kind of geometrical language to extend this construction to general expanding background. Okay, so the ingredients, of course, we can use a metric and inverse of the metric and curvature, Riemann curvature, and covariant derivative constructed from this metric as usual. But on top of that, we can use time because time is invariant under this. We don't change time. Okay? So we can use time in the action. So the action can depend explicitly on time. Okay, in this analog of this which one? Yeah, unitary gauge description. Later, if you want, we can recover diffeomorphism by introducing redundant degree field. Okay, but at first we can construct the action in the unitary gauge where we have only special diffuse. Then the time can be used. Also, we can use a derivative of time. Okay, for example, if we take a first derivative of time, then we get the Kronecker delta. Okay, and also we can construct a vector, a unit vector, which is normal to constant time surface. Okay, this is proportional to derivative of time, but we need to normalize. We can also normalize by using first derivative of time. Okay, so this is a unit. These are the unit norm. Okay, NMU has is -1. Okay, and also we can use G00 upstairs because this is just G mu nu contracted with two of these. Okay, so we can use G mu upstairs, but not downstairs. G00 downstairs cannot be used, but the G00 upstairs can be used in the action. Okay. Also, we can construct H mu nu, which is this combination because N mu is given by this, and this is nothing but 3D metric constructed on the constant time surface. Okay. If we contract this with N mu, because N mu is -1, which give us 0. So that this is orthogonal to N mu. Okay. And so this is induced metric on the constant time surface. Okay, we can also introduce the second derivative of time. And because N mu is already first derivative, we can introduce a derivative of first derivative. And then the project onto the constant time surface. This is nothing but extrinsic curvature. This is a completely nonlinear extension of this quantity. As I said, this is a tensor in 3D constant time surface. So this is good. Okay. So the action can be constructed by these ingredients. So in general, we have some integral over space-time of some scalar quantity. Okay. Scalar quantity is written in terms of time, Kronecker delta, and K mu nu, a Kronecker delta with 0 upstairs, of course, and extrinsic curvature, metric, inverse of the metric, covariant derivative, curvature. And this is completely general, and it's okay, but this is too general. So that it's nice to have some finite number of terms. In order to do that, we need to do some derivative expansion and the perturbative expansion. Okay. Around the Friedman, Lemaitre, Robert, Thompson, Walker background, homogeneous isotropic background. Then we introduce difference of G00 upstairs between the general background and the Friedman background. And same for extrinsic curvature and 4D curvature. And then by introducing derivative expansion, we have this kind of expression. The first term, after doing some change of variables, is Einstein reduction. Okay. Second term is just a function of time. And third term is a function of time multiplied by G00 upstairs. We can use the G00 upstairs here because this is, as I said, contraction of this with two of this. Okay. And some more terms which are a bit complicated. Okay, written in this way. but this is completely general. Then, as we have done for around Minkowski background for ghost condensate, we can introduce Lamb-Gosson boson by undoing unitary gauge. So we can just replace, introduce new time coordinate T tilde, and then the substituting T equal T tilde plus pi, which is function T tilde and x. Then but after doing that, we can rewrite T tilde by T for simplicity of notation. Okay. And then this means that we can just replace h of t by h of t plus pi and so on. Okay. And Kronecker delta is transformed in this way by plugging this transformation, as we did for ghost condensate. In the case of ghost condensate, we substituted them, this to here, and here, and we get this. Similarly, we can undo the unitary gauge and then substitute these expressions to here and there, everywhere. Then we get this. Okay. After then yes, in general we have this with this replacement. But then after that we can go to the so-called decoupled limit, where we ignore the perturbation of metric. This makes computation very easy. Then we have just pi, Lamb-Gosson boson. Okay, the action is given by this. Here, this CS square defined by this represent the so-called sound speed square, because dispersion relation of pi is given by this. Okay, pi dot square is multiplied by this, and okay, pi dot yes. Then the pi, so gradient square of pi is multiplied by same coefficient times minus CS square. So the dispersion relation is like this. Indeed, CS is the speed of propagation of this pi. Okay. Now we can go on to include the higher order term, higher order in pi, terms higher order in pi. So this is just application, and then we find that there are only two terms that are important at the level of third order. Okay. Then from these two terms, we can compute power spectrum, and we can convert it to curvature perturbation, which is directly observed by CMB observation. And then from these two terms, we can compute non-Gaussian 3-point function, for example. And then we can compare with observation. Okay. And what is interesting that we have only two terms, and a priori we may have many terms, because so non-Gaussianity means not Gaussian. So whatever is not Gaussian is non-Gaussian. So the infinite number of possibilities, but we have only two terms. So we have only two kinds of non-Gaussianities. Okay. Then one of the coefficient, so one combination of two coefficients determines the size of non-Gaussianity, because 3-point functions, size of 3-point functions are basically characterized by these two numbers, so-called nonlinear parameters, which becomes large when sound speed square is small. Okay, we have the inverse of sound speed square here and also here. Okay, so the sound speed square is characterizing the size of non-Gaussianity, and another constant, because we have only two terms, we have two parameters. Another parameter characterizes this the shape of non-Gaussianity. Okay, this is the shape of 3-point functions, and when C3 is 0, we have this kind of shape, and when the C3 is of this value, we have this kind of shape. For any other values, the shape is linear combination of them. So the non-Gaussianity at the level of bispectrum or 3-point functions is characterized by just by two parameters. Okay. This is thanks to the effective field theory. Okay. So let me summarize effective field theory of scalar tensor theory. So the ghost condensation is a universal description of scalar tensor theories around Minkowski background or Dojita background. And the extension of ghost condensate to Friedman-Lemaitre-Robertson-Walker background results in the effective field theory of inflation or dark energy. And this effective field theory provides a universal distribution of all known scalar tensor theories, including Hornby-Disk theory, dorsal theories, and more. Okay. I think this is the end of this section and end of today's lecture. So I'd like to accept some questions if you have.
Thank you very much. So yes, let us take some questions. I'm sure there are. Yes, one from Luis Longo, please.
Hello. First, thanks for the very nice talk.
Thank you very much.
I was wondering, you did this effective field theory in the case of flat space-time and the cosmology case. Can you do this, for example, around a black hole, as you said, for a strong field, and what is going to be changed? Because there, I think that the assumption of being a isotropic space will drop, so something will be less constrained, I guess.
Yes, I think yeah, we need to change this assumption. Okay, so that we need to specify the symmetric breaking pattern. Yes. Then yeah, that's so construction changes. Yes, but I think in principle, in practice, we may have a lot of too many terms, but in principle, if we specify, say, spherical symmetric black hole or rotating black, asymmetric black holes, then in principle it's possible. But in general case, say yeah. So say yeah, it's symmetry is so we have less symmetry. In other words, if we reduce the amount of symmetry, then we have more terms. More terms mean more parameters and less predictive powers. But at least we may be able to find some parameterization of what is known, maybe. Yeah.
Okay, another question from Gabriel Luz Almeida.
Hi, hello. First of all, thanks for the very nice talk. So earlier in this, so earlier in this lecture, you mentioned the possibility of adding another metric tensor, and I was really curious about this. So by any chance, would you have some examples of theories that use this idea, and possibly talk about a little bit about the physical consequences of this?
Maybe yes, if I have time. So that actually, so yes, I don't have, maybe I can go to the this table of contents. So the in section 5, actually tomorrow I'm going to talk about massive gravity, and at the end of this section I may talk about the so-called bigravity, where we have two metrics.
All right, okay.
So we have not only one metric to which the matter couples to, we have another metric. So that is not forbidden by Einstein's, so yeah, Einstein's equivalence principle. Yes.
Okay, thanks. So this is going to be next lecture, right? I think
that's
tomorrow.
Right, tomorrow. Yes.
Okay, thanks.
Yeah. But the main focus of this section 5 is massive gravity. So we have just one metric. But at the end of the section, I may touch on bigravity briefly.
Okay, thanks.
Thank you. So another question from Zakaria Belkadria.
Yes, do you hear me?
Yes.
Yes, I do.
Yeah, so I have two questions. The first one, just to follow up about your answer from the Einstein gravity. There was a paper last year, consider this theory. You can see it when we do the compactivation as Hornby theory. So we can interpret it as having an extra degree freedom. But you said the only consistent way is to break Lorentz invariance. So which So which one do you consider for the the consistent? Is it just having extra degree of freedom and we see it as Herdensky, or we need to break time determinants? The second question, how we could map EFT theory with Herdensky and with those, like, can you show it? I know that it's possible, but I don't know how we can do it.
Okay, so I
yeah, thank you.
Not hear very well, but the first question about the 4D Einstein-Gauss-Bonnet?
Yes.
Okay, yeah. So actually, I worked on that. Yes, so the yes, so there are some proposal of 4D Einstein-Gauss-Bonnet which apparently contradicts with Lovelock theorem, but because Lovelock theorem is theorem. And actually, I followed all the proof, and I agree. And so we need to break assumption, okay? Or we get some different conclusion. And okay, anyway, so the original proposal was to consider this Lovelock, actually the Einstein-Gauss-Bonnet. So the first two terms plus cosmological constant, and in higher dimension, n dimension, and then if we take the four-dimensional limit, of course, then the Einstein-Gauss, so this Gauss-Bonnet term becomes total derivative. So does not contribute to the equation motion. Okay, this is consistent with the Lovelock theorem in four dimension, because the Lovelock theorem is about statement about the equation motion. Okay, so equation motion. So this term does not contribute to the equation motion in the n equal 4 limit. Four-dimensional limit, okay? But original proposal of this 4D Einstein-Gauss-Bonnet is just consider, say this coefficient, okay, alpha in this case, A2, A1 is a coefficient of Einstein-Hilbert, and A2 is a coefficient of the Gauss-Bonnet, okay? So A2 is divided by, in this case, n minus 4. So the coefficient, I mean, so the numerator in the equation motion goes to 0, and then the divided by 0, then maybe 0 over 0 may goes to 0, go to some finite number. That was the proposal for the Einstein-Gauss-Bonnet. But if we preserve for the diffeol, then because Lovelock theorem is a statement about equation motion, we cannot break it. Okay, so we need to break either. So we have some inconsistent theory where we have a kind of scalar tensor theory, either scalar tensor theory with infinite strong coupling, or we need to break time diffeol. And only non-consistent for the Einstein-Gauss-Bonnet theory with a 2-degree freedom is a broken time diffeol that actually I constructed. So you can have a look at my paper if you want.
Okay, so the next question is from Barry Ginat. Sorry.
Yeah. Thank you, but that was the second question about.
Sorry.
Yes, that's right. Yes, I forgot. Yes.
Yeah.
The second question is about.
Me too.
What? I didn't hear you.
The EFT and Herdensky, and how to map EFT theories with Herdensky theories.
So about EFT. Okay, so then.
Yeah, how from EFT theory we can go to Herdensky? Or from Herdensky theory. So I know that there is mapping between two.
Sorry, we cannot hear you well.
Can you write your question?
Okay.
Yeah. Meanwhile, I can. I mean, so other people, if you have ask questions, then please. Meanwhile. Yes, please write your question in the chat.
Yes, we can take Barry Ginat, for instance. Please ask your question. Hello? We cannot hear anything. Okay.
I don't hear. But I
Please,
now
Barry.
see the
Okay,
chat.
so
yes, question is about the mapping
so
between EFT and Herdensky and the DOST. Yes. Yeah. So yes, yes. So the not here. Okay. So the for example here or maybe here, maybe here. Okay. So the there are many terms, and so we can compute the for given theory we can compute those coefficients, because so once we know the theory, we can go to this unitary gauge. Okay, so we can set the okay, not here, but so we can set the phi. Say we suppose we have a scalar field phi and g mu nu, then we can set phi to be function of time by hand, and given function of time, then plug it to the given action, fundamental action, say Horndeski or Dost or whatever. Then expand in this way. Then we can compare the action obtained in this way with this. Then we can compute the coefficients. And there is a kind of dictionary between theories and these coefficients. I didn't show you, but in the literature there are some tables or dictionaries.
Okay, it seems that the microphone of Barry Ginat works again. So can you try to ask your question?
So it is working now?
Yes.
Yes.
Good. So sorry about that. Thanks for the lecture. And my question is if one can use the EFT of scalar tensor theories to derive the equivalent of PPN parameters for a cosmological background, and then get constraints on them from cosmological observations as well?
Yeah, sure. Yes. In the case of inflation, that is what people do here. Yes. So as I showed you here, so there are two parameters, and one combination controls the size of non-Gaussianity, and other controls the shape of non-Gaussianity. And from observation, we can constrain the amplitude of non-Gaussianity. Then this can tell us directly we can get the constraint on the value of these parameters, sound speed and this C3. And then from the theory, given theory, Dost or say K-sense or Horndeski, we can compute these coefficients. Then we can constrain these theories. And also for the structure formation, we can do, I mean, here I show the construction of EFT of inflation, but we can do the same thing for the EFT of dark energy. And then we can consider correction to the structure formation, for example. Then in principle, we can constrain the coefficient of this EFT action.
Thanks a lot.
Okay, I would like to say also that there are comments in the chat about PPN parameters and mapping between EFT and Horndeski with references. So you can have a look. I mean, everyone can have a look. I think if there is no more question, it's a good time to stop because I mean, there will be some opportunity to ask more tomorrow, I guess, in the next lecture. So thanks for your participation. Thanks again to Shinji. And we will resume this afternoon with the session on gravitational waveforms starting at 4. So this afternoon, of course, for us in Europe, but I guess in Japan, it will be a bit late. Okay, that's the problem of time shift. So anyway, see you later. Goodbye and goodbye.
Yeah, thank you very much. Hi, Filippo.
Thank you, Shinji. Hi. I think we can stop the recording. On peut arrêter l'enregistrement. Guillaume?
C'est plus moi qui est...
D'accord, je l'arrête.
Ouais, merci.
Bon après-midi.
Au revoir, merci.
Merci.
Et Guillaume, cet après-midi, tu veux que je commence?